Hi, in this video I'm going to go through analytical techniques. So the two we need to look at in first year is infrared spectroscopy and mass spectrometry. So we'll start with infrared spectroscopy. Now, infrared spectroscopy takes advantage of the fact that the wavelength that infrared exists at can be absorbed by certain molecules. Specifically, usually it can, well, not molecules but bonds. It can be absorbed by the CH bond, the OH bond, the NH bond, COO bond, and the CCC bond. There's other bonds as well that it cannot absorb this energy, but these are the ones that we need to kind of focus on. And the most important ones for us are the CH, the OH, and the COO. So, infrared light gets, whenever it passes past any of these molecules, it causes them to absorb the energy and they vibrate and bend and shake a little bit inside the bond. It starts to move around, but that absorbs the energy. And so this is a big leader to greenhouse gases. And this absorption of energy creates the greenhouse effect. So specifically in compounds that have these bonds. So for instance, methane is a greenhouse gas because it's got CH bonds. Water, you get too much water, that's a greenhouse gas because it's got the OH bonds. And probably most famously, COO. And so COO, the carbon dioxide, that's very prevalent at the moment in the atmosphere. There's about 200 times as much carbon dioxide as there is methane. So there's a bit more of a danger with the greenhouse effect from carbon dioxide. Also, CFCs get a bit of an issue with. CFCs we looked at earlier in haloalkanes, chlorine fluorocarbons, and they absorb infrared light, and their problem with them is that they stay up there for years and don't tend to break down. But we can take advantage of this property in analysis. And what we do with the compound is we replicate that UV light. So we shine UV light, UV infrared light at different frequencies, and we get a little graph. That will be its transmittance. So that's going to tell us how much of the infrared light gets through and the wavelength. So infrared operates between 400 centimeters cubed to the minus 1, so 1 over 4,000, sorry, and 500 centimeters to the minus 1, not centimeters cubed, centimeters to the minus 1. So this is 1 over 4,000 and 1 over 500. So if we were to shine infrared light and there was no molecule there at all, we just get a straight line as all the light goes through. Now if we put a molecule there, the bonds start to absorb, and we get different bonds will absorb a different wavelength of infrared light, always at the same point. So then we can start to identify. So we start to get bits that look like this. We might get these peaks, and now these are where here no infrared light being absorbed, here suddenly infrared light's been absorbed, so there must be a bond there. Then we go down, we get nice big broad peaks that are specific, and then as we get closer to 500 centimeters to the minus 1, we start to suddenly get what we call the fingerprint region, where we get lots and lots of peaks and it's difficult to distinguish. But in these peaks that we have here, we have got some clear ones. We've got at about 3,000 to 3,200 a broad peak. You've seen all these are quite sharp, they come down, go quite sharp, but when you get a nice broad one, because of hydrogen bonding, that's usually an OH. Could be an NH, but it's usually at this level. An OH. Just below the OH peak, we get generally lots and lots of peaks, all kind of overlapping because we get lots of CH bonds in organic chemistry. And now at almost precisely 1700 centimeters to the minus 1. Between 1600 and 1700, we get a very broad peak coming down, and that's our COO peak. So we can look at this compound and we go, well, this one here has got a COO and it's got an OH. So that could be either something with, say, a ketone or an aldehyde with an OH alcohol group on it, or most likely is what you've got here is a carboxylic acid. It could be either one of those things, but it's one way we can identify functional groups on different carbons, on different organic compounds. So put them in here, we can see where they absorb to get us different compounds. So if we didn't have this here, if that was just straight there, go, well, it's probably an alcohol. Could be an amine, probably an alcohol. If we had that missing completely, probably go, it's an alkane or an alkene. If we had that missing, put that peak there, then it's got a COO, and it's probably a ketone and an aldehyde, but it won't be a carboxylic acid because there's no OH there. So infrared can be used to identify lots of different things like that. It's used in real life. We use it in breathalyzers because it can identify alcohols, and car emissions where we're trying to identify CO and NO coming out the back of car emissions. So the second technique you need to know is mass spectrometry. And how this works is we put our molecule into a little capsule and we blast it with electrons, and that smashes it all up and ionizes it. And once it's ionized, we can put it through the mass spectrometer and it can get attracted to a magnet and we can manipulate it, but it tells us the different masses of all the parts of the compound. So for instance, let's say we had this molecule and we put it into a mass spectrometer. Now that gets blasted with electrons and forms ions, and we might just form this ion. So they are, we're blasted with electrons, generally forms positive ions. We've got a positive molecular ion, we call this, because it's the molecule that's just been ionized. It could be that we get bits split off, so we could get a nephal where we've had a splitting just here. That would also, you see, give us a splitting there where we have CH2OH, or just an OH plus where this is split. So we get lots and lots of different splitting. What we wouldn't get, and would be a mistake to say we get, is to have C3OH plus, because they're not joined together, and so you wouldn't get this splitting. What happens is they go through a spectrometer and they get to a detector which reads their mass to charge ratio. It is possible we get 2 plus ions and that affects the mass to charge ratio, and the abundance that we have of them. So if we get a lot or not. So in this case, our mass to charge ratio would start at 0 and it go up to, say, 50. And at 46, so that's 45, at 46 we get a reasonably large peak. And that's because this mass, added all up, is 46. And this is known as our parent ion peak, our molecular ion peak. So the last peak on any mass spectrum generally tells us what the molecular mass is of the compound. But we get a peak here at 15, a peak here at 31, that's probably quite a big peak, and maybe a peak at 17 as well, quite a small peak there. There'll be different sizes, but we'll start to get peaks all over. We'll also get, annoyingly, this makes it a bit difficult, isotope peaks as well. So the peak at 46, we're assuming that all the carbons are carbon-12, but we know carbon exists as carbon-13 and carbon-14, albeit in very small percentages, especially carbon-13, but so carbon-14. But there is a small amount of carbon-13, so you might see a very tiny peak straight after the M peak. And this is the parent ion plus 1 peak. And it's not to be taken as the molecular mass. But we could see from, if we put an unknown into a mass spectrometer, we'll be able to find out its molecular mass by finding this peak. We could then also find out, or have an estimate of what's in there by looking at how it's split up. And so we can combine these two techniques, and if we combine them, we can then start to identify, one, what type of functional groups we have, and then what is the molecular mass to kind of identify the compound. So let's take a quick example of this. So excuse my drawings. If we take infrared, that looks a bit like this. Not a great scale I've used here. And then a very quick mass spec that has the parent ion, so it is at 60. The M plus 1 about there, peak at 15, peak at 31, peak at 46. So what we do is we look at this and go, right, here we've got an OH peak, possibly an NH peak, and we can rule out either one of those in here, in your mass spec. Then we've got CHs. This is the fingerprint region. And what we could actually do here is just stop and try and compare this to a database and compare the fingerprint to a database, and that could identify the compound for us. But if we can't, then go, well, we've either got here an alcohol or an amine. So if we had an alcohol, we'd expect peaks at 17, probably one at 31. And that is, we've got the OH peak, and this is the CH2 OH peak. Now if we've got an amine, we expect peak at 15. Now that's a tricky one because CH3 plus is also at 15, but you'd expect one at 29 from the CH2 NH2. So we can look at this and go, well, early on we saw that this was 31, so this is an alcohol. And then we need to identify what alcohol has a molecular mass of 60. And we can rule out methanol. So that's 32. Ethanol, 46, as we saw earlier. So this must be propanol. 3 carbons, 36, 39, 41, 43, 44, and an oxygen take up to 60. So we can use it then to identify that this rough infrared mass spec must be propanol. And that's first year analytical techniques.